Network delay time is probably the most direct uh, application of Dijkstra's that you can find on lead code. I did have this in mind when I made the videos on advanced graphs. So, but I couldn't explicitly refer to this at that time. So hopefully this should not look, the code for this shouldn't look too different from what I had in the videos. So the problem is as follows. You're given a network of n nodes labeled from 1 to n, and since it's a network, it is a graph. So the IDs are from 1 to n, not 0 to n minus 1. And then you're given an array called times, which is essentially an edge list. It's a list of directed edges, which means this is a directed graph. And the interesting thing about this graph is that it's a weighted graph. So the individual edges in the edge list are not just source destination pairs, they are triplets. And the third element in the triplet corresponds to the weight of that particular edge. So that means we are looking at the edge from ui to vi with weight wi when we consider the ith edge in the edge list. So we are going to send a signal from a given node whose ID is k. So k is a vertex in the, its value will be some value from 1 to n. And we are actually sending a signal from the given node k, or as I discuss in the videos, imagine a virus that starts spreading from node k, and let's say it radiates out from node k at a speed of 1 unit per day. So if we imagine the weight on the edge or each edge as the length of the path from u to v, and let's say the virus takes that many days to reach v from u, it takes w days to reach v from u, then we want to essentially return the time it takes for all the nodes to fall sick. And if it's impossible for all the nodes to receive the signal, if it's impossible for them to all fall sick, then we return a -1. So in this toy example, uh, this is the input array. We are given 4 vertices in the graph with IDs from 1 to 4, and we start spreading the signal from vertex 2. The edge from vertex 2 to vertex 1 has a weight of 1. That's what the first edge is. The edge from vertex 2 to vertex 3, sorry, 2 to 1 is this one. This edge has a weight of 1. The second edge is the edge from 2 to 3, which also has a weight 1. The third edge is the edge from from vertex 3 to 4, which also has a weight of 1. And we want to find out how many days it will take for all the nodes to fall sick. So in this particular graph, vertex 4 is going to fall sick on day 2. Right? Vertices 1 and 3 get the signal on day 1. Vertex 4 gets the signal on day 2. And all the nodes get the signal at the end of day 2. So the output is 2. If there was only one edge in the graph and there were only 2 vertices, and with IDs 1 and 2, obviously, the edge from 1 to 2 has a weight of 1. And if the signal is started from vertex 1, then in one day, node 2 will fall sick, which means at the end of day 1, all the nodes in the graph are sick, so the output is 1. But if in the same graph, the direction of the edge had been reversed, that's the third example, then a signal that starts from vertex 1 is unable to reach vertex 2, which means that there is no particular day when all the nodes fall sick, so the output is supposed to be -1. So K is the vertex from which we start sending the signal or we start spreading the virus is a valid vertex in the range from 1 to n. And um, the source, each edge is a triplet and there are no self loops in the graph. So that means the source of each edge and the destination of each edge are different. Shouldn't be a surprise. And there are no multiple edges. So I assume that you all see that this problem directly maps to Dijkstra's. This problem essentially is the shortest path problem. We want to find out uh, how long would it take for the signal to propagate to all the vertices. And if you take the virus analogy, each vertex is going to fall sick along the shortest path from the source vertex to it. So the length of the shortest path from the source to any vertex will also be the day number when the vertex falls sick. And so we want to find out um, how long does it take before everyone falls sick, right? So the vertex that is farthest from the source in the original graph will fall sick at the very end. And once that happens, once that event happens, the particular day on which that farthest vertex fell sick, that would be the answer to our problem, assuming that no vertices were spared. Now in these toy examples, the weights on the edges were all 1. And we know from our graphs live class that if all edges have the same weight, then breadth first search also works. But these are toy examples, and it's not necessary that more complex examples would have a weight of 1. So in general, this is going to be a weighted directed graph, which means we cannot assume that BFS will give us the answer. As a simple example, if we have, say, a 3-node graph like this, I had this in the videos. If we have weights like 2, 5, and 2, then vertex, and let's say the source is vertex S here. If we do BFS would tell us that both U and V are 1 hop away from S, and so they are they are at equal distances from S. But if we look at the weights on the edges, we see that the 1 hop path to V from S is actually more expensive than the 2 hop path from S to V through U. It has a weight of 2 plus 2, which is 4, which means vertex V is going to fall sick on day 4, not on day 5. And so our algorithm needs to return this 2 hop path from S to V instead of the 1 hop path that BFS would return. And that is why we use Dijkstra's algorithm for it. So I'm going to code this up since there's no mystery about what algorithm uh, this is. Uh, as long as you understand what the problem is. Any questions about the problem description? For example 1, why is the output 2 and not 3? Well, because the on day 1, 1 and 2, 1 and 3 will both fall sick, and at the end of day 2, node 4 falls sick. So it takes 2 days for everyone to fall sick. That's why the output is 2. Do we need n here? It seems we can infer it. Well, it depends. We may not be able to infer it if some of the edges don't refer to n, right? Uh, if there are vertices that don't have any edges incident on them, we don't know what their IDs would be unless we were given that information separately. That's why we need that. It asks for all the nodes to receive the signal, not the shortest, still Dijkstra's. Well, how will all the nodes receive the signal? Right, the point is the signal will be received from along the shortest path. Right, it says return the time it takes for all the nodes to receive the signal. It's not asking whether or not all the nodes will receive the signal. Then if the question was whether or not all the nodes will receive the signal, then that would be a standard DFS or BFS problem. The time it takes for all the nodes to receive the signal has to be the earliest time when everyone falls sick. And that's why this is a um, shortest path problem, right? Not just a regular DFS problem. Why not BFS? Can you explain again? So, folks, I'm sorry I won't be able to explain like things which I have. If you haven't seen the videos on Dijkstra, I would strongly urge you to drop out of this class and watch the videos, because um, there should be no confusion about the fact that Dijkstra is what we would use here. And but still, for the last time, I'll just explain on this 3-element graph. You can see that vertex V and vertex U are both one hop away from vertex S, and breadth first search would create a BFS tree which has U and V as direct children of S. And that means both of them would be at level 1 in the tree, and that's not what we want. We don't want, the answer is not 1. The answer is should be 4, because on day 2 vertex U will fall sick, assuming that on day 0 the source is already sick. On day 2 vertex U will fall sick. On day 4 vertex V will fall sick. So the answer for this graph needs to be 4, right? 4 on day 4 everyone falls sick, and there is no way BFS can return this answer to us. We need Dijkstra for it. This was, by the way, the example I had in the videos. So whenever our graph is weighted, we can't use BFS for shortest paths. Okay, so I'm going to write the code for Dijkstra's algorithm similar to what I wrote in the. I'm going to treat those videos as foundation videos for this class. The advanced graphs extension material, basically foundation videos for today's class. So similar to breadth first search, um, we want to first build a graph, right? Our code is going to have in general 3 parts for a general problem. Um, so let's start with the first part where we build the graph. We want to build the graph from the edge list. This looks familiar. So we are already given n, which is the number of vertices with IDs from 1 to n. Okay, and we are looking at, we want to build the adjacency list by looking at the edge list. Since our vertices are in a convenient range from 1 to n, our adjacency list will be an array with indices from 0 to n, where this is going to be an unused index. So this list will be the adjacency list for vertex 1, this will be the adjacency list for vertex 2, and so on up to vertex n. This is what we have to build. So the adjacency list starts out as a one-dimensional array of size n plus 1 initialized to a bunch of empty lists. Empty lists, and these are not, so unlike unweighted graphs where these lists were lists of integers, right? Each list here was a list of integer IDs corresponding to the neighbors, the direct neighbors of whatever vertex we are looking at. But here, now we are going to have each element in the adjacency list be a pair, right? It's going to tell us who the direct neighbor is, but also the weight of the edge to that neighbor. So lists of integer pairs, you can say, right? So each pair will be of this form: the neighbor ID followed by the weight of the edge to that neighbor. So how do we fill up? How do we construct this part? In a similar way as we were doing for unweighted graphs, we parse all the edges, individual edges in the edge list. So the edge list has a name. um the variable name is times. So um, we will just iterate over each triplet in that edge list. So for source, comma, destination, comma, w, comma, weight in the edge list, this is a directed edge. So what we need to do is add an edge from the vertex corresponding to the source to the vertex corresponding to the destination with the weight w. That means we go to the adjacency list for the source and we add or append the destination node, right? This is what we were doing for regular unweighted graphs, but this time we have to append a pair, not just the destination ID, but also the weight of the edge to that neighbor. And since this is a directed graph, there won't be a reverse edge from destination to source. This is all we have. And apart from these two, uh, we don't have anything else. Our graph is kind of built. Now for BFS DFS problems, we used to have a visited array, which would also be initialized before we launch the breadth first search, depth first search functions. For Dijkstra's algorithm, we are not going to have visited array. Instead, we are going to have an array called captured. And again, I'll refer you back to the foundation videos if you don't uh, remember this or if you haven't seen them. Essentially, the word visited, as I have discussed in my live class, uh, is kind of a confusing word. A better word for it would have been discovered, because in the general graph traversal algorithm, which I have talked about in the foundation videos, remember we have all the vertices initially undiscovered on the right side, right, as if they lie in a deep blue ocean. And then we are given the source vertex S to start with on the left, and the vertices on the left, they are what we call as captured. So it's as if the set on the right is a set of fish in a deep blue ocean, and the set on the left is the set of fish that are lying on the beach sand. And we are like a fisherman. We initially start out with one fish in our hand, which is the source vertex S. From there, we look at all the outgoing neighbors and we discover that there are fish. There are actual, fish that are swimming in this ocean, which we didn't know about. We discover them. And as we discover these fish, which are direct neighbors of S, we pretend to capture them, not capture them, sorry. We mark them as discovered by putting them inside a fishing net, which is some kind of data structure. In breadth first search, it would be a queue. In depth first search, it would be a stack. In Dijkstra's algorithm, it would be a priority queue. So this discovered set is what we mean when we use the word visited. We know about the existence of these vertices. We don't know about the existence of these other vertices which are still swimming deep in the ocean. They are still undiscovered. And once we pull out an edge from this discovered set, which is either a BFS queue or in Dijkstra's algorithm, the priority queue, we drag it ashore, and that vertex becomes a part of the set of fish lying in the beach sand, which are denoted as captured. So we keep capturing more and more and more of these vertices until we get a tree on the left. This is not the BFS or DFS tree. This is the shortest path tree when it comes to Dijkstra's algorithm. The shortest path tree would have shortest path distances from S to every vertex in that tree. Okay, so why is it that we don't need a visited array and instead we need a captured array? Does anybody remember that from the foundation videos? Just raise your hand. Yeah, Melvin?
Because we are not all the discovered ones are going to be captured. It's only the a subset.
So this algorithm continues until our discovered set is empty, like we have had for breadth first search as well.
Yes.
Which means once a vertex is discovered, there will come a point. If you look at the life cycle of a typical vertex, it's going to start out swimming deep in the ocean. It's undiscovered. At some point, it is discovered when one of the vertices on the left uh, is examined, its adjacency list is examined, and all its neighbors are examined. We are going to see a hook going from this fish to a new fish which was so far undiscovered, at which point that fish gets added to the discovered set. And this process continues until the queue becomes empty. Right? In Dijkstra's algorithm, the priority queue, which holds all the visited or discovered vertices. So that means once a vertex becomes discovered from an undiscovered state, there it is going to continue existing there until there comes a point when we drag that vertex out and capture it. So these are the three states through which a typical vertex goes through: undiscovered, discovered, and then captured. So every discovered vertex is going to be captured at some point. But we don't worry about this captured notion with breadth first search. Although we could, but it doesn't add anything to us there. Why does that change in Dijkstra's? Why is it that we, instead of worrying about visited, we start worrying about captured? So Shankar Narayanan.
Yeah, so the reason is because the time we mark something visited is not going to be the same time as when we mark it captured. So that's why we need, like, we can't just have a visited. That's the reason we can have just a visited array.
But that's true even for BFS, right? The time at which a vertex is added in the BFS queue is not the time at which it's going to be pulled out from the queue. Okay, let's see. Anyone else? Alexandro?
Yes, when you capture a node, that's already the shortest path. You already found the shortest path. But in BFS, when you visit it, that's the shortest path.
Yeah, exactly. So in breadth first search, when you discover a vertex, you always discover it along the shortest path, which means that when it's added into the BFS queue, at that point of discovery itself, you know what the shortest path to it is. And so even when it's later dragged out and captured, uh, that's not adding any, there's no new information there, which you didn't know already. In Dijkstra's algorithm though, when you discover a vertex, you add it to the priority queue with a priority value that corresponds to the length of the path that was used to discover that vertex. And that path need not be the shortest path. It's just the first path through which you discovered that vertex. So as the vertex lies in this discovered set, it's possible that its value for the shortest path could change, could be updated. It could become smaller in size, small in magnitude, as you find some new path to it. And so its priority value can keep changing as it's inside this discovered set, and it's only when it's pulled out. When is it pulled out? When its priority value becomes the least among all the priority values for the other vertices in this discovered set. At that point, when you pull it out, that is the point when you know what the shortest path distance to that vertex is. That is the point where it's finalized. And so it is the captured set that you have to look at to decide if the vertex is the shortest path to it is finalized or not visited. In BFS, looking at visited was sufficient because if it is visited, you also know at what distance it lies from the source. But here it's only when it's captured that you know. So that means even if it's visited or whether you are discovering it for the first time, these two events are not fundamentally different, because in either case, the shortest path to that vertex may not have been finalized. Now, I mentioned that the shortest path to a vertex might get updated in the course of running of Dijkstra's algorithm, as discussed in the videos. So what was the way in which we are supposed to implement this? Because the problem is, when the priority value of a vertex is updated, you have to change its priority value in the priority queue, which is going to be a heap for you. So that is not possible when you use a library heap. So what is the solution for that? Does anybody remember? Paul?
Oh yeah, there are two solutions you discussed.
Mm.
One was you enter the node again with lower priority, and the heap will take care of it.
Yeah.
Other one was you keep a reference to the node in the heap and then bump up the priority.
Yeah, so that reference solution is more complicated. It will
Correct.
require us to implement, a
Yes.
more complex type of heap with those references and all. So for that reason, what we did is, or what I'm explained in the video is, we will keep reinserting multiple copies of that vertex
Yes.
into the priority queue when we find that its priority value has changed. Instead of going and changing its priority value in the discovered set, we'll actually add another copy of that vertex with that lower priority value.
Yes.
So that means when that vertex comes out and it's pulled ashore, it's coming out with the smallest priority value. If there are 5 copies of that vertex lying here, the copy that first comes out is going to be the copy with the smallest value for the shortest path distance, and that is its true value. So that means after that, we might have to subsequently look at outdated entries when we pull out those remaining 4 copies at a later point. We just have to ignore them since that vertex has already been captured. Right? That's why the captured array is relevant. The visited part is not relevant, because regardless of whether or not that vertex has been visited or whether it's undiscovered, we are going to add a copy of that vertex into our heap with some priority value. So it doesn't really matter whether or not it's discovered or undiscovered. And it's for that reason that we don't worry about the visited set. We worry only about the captured set. So what therefore I will do here is I will also have an additional array, just like we used to have the visited array for BFS. I will have a captured array, which is going to be a one-dimensional array of size. Normally it would be n, but because here our vertex IDs are from 1 to n, we'll have an extra unused entry in this array, initialized to -1. Right, so that's our initialization. And then in the second part, we used to implement BFS or DFS. Here we are going to implement Dijkstra's algorithm. And for Dijkstra's algorithm, we would typically not have an outer loop because we would be given a single source. And so we have to always launch Dijkstra's algorithm starting from that source. Unlike BFS and DFS, where we would have to explore the whole graph to discover some properties. So we won't have an outer loop. So we don't even need to write Dijkstra's algorithm as a function because it's going to be called only once. So there's no point in writing it as a function. So we will do what we were doing with breadth first search. We will have a new, we'll initialize a queue, but this is going to be a priority queue or a min heap with, well, initially we can start out with it being empty, but we will basically have to insert or push into the queue the source vertex itself. But, and this is also what something we did with BFS, but the source vertex here, which is given to be the vertex K in our lead code problem, is not going to be inserted in a standalone way. It will be inserted with some priority value. And since the source has a shortest path distance of 0 from itself, that is something we know beforehand, we will insert the source vertex with a priority value of 0. Now, when inserting it into the priority queue, we won't insert it as a pair source comma 0. Instead, we will insert it as a pair 0 comma source. Why is that? Because when we compare two different elements in the priority queue, our library heap is by default going to look at the priority value first, right? The vertex IDs don't really matter. So we don't want the sorting or the ordering, relative ordering of the elements to be based on the vertex ID. So we make it the second element of the pair. It's the priority value which needs to be the first element of the pair. So that's how we start out. That's our initialization. Parallel to BFS, right? And parallel to BFS, we say as long as the queue is not empty, as long as the priority queue is not empty, what do? Well, we pop the next element from the priority queue. So q dot, you can say extract min, right? Instead of q dot pop, I could have written q dot pop, but just to make it clear that this is a min heap we are talking about, let me write it as q dot extract min. And this value, what we extract is going to be a pair. It's not going to be just a node, it will be a pair. So in particular, it's going to have some priority value associated with it, which is going to be some tentative shortest path distance to that node apart from the node itself. Right? So the node is going to come out with its corresponding priority value, which is the length of some tentative shortest path to it. Now, as I said just a few minutes back, there could be multiple copies of this node in the priority queue, and it's the first copy that comes out that is the relevant one, which is what leads us to capture that node, not subsequent copies. So that means if this node is already captured, right, that means the captured value for that node is not -1. Right, it's been captured, that means its value would be set to 1 or something else. It's not going to be its default initial. So this is like saying the node is not visited in BFS. Here we are saying if the node is not, if the node is already captured, in BFS we would check that the node is already visited. Here we are checking if the node is already captured, that means this is a later copy of that node. We just ignore it. Right? We are interested only in the first copy of that vertex which comes out. So if it's some subsequent copy, we're just going to ignore it. And if it turns out that this is the first copy, then we'll come here. So this is the point where we capture that node. We set its captured value. Ordinarily, we would set it to 1. But I'm going to do something that I have done for BFS problems also, which is I deliberately set the captured value to -1 here so that we can reuse this to store not just the fact that it's captured, but also specifically what the shortest path distance to that node is, which we know, which we can finalize at the moment of capture. So I will not just say that this is 1, I will set it specifically to the value of the shortest path. Which has to be a non-negative number. Dijkstra's algorithm runs only on non-negative numbers. It doesn't run if the edges have negative weights. So we will. So what's the shortest path distance to this node? Well, that's the priority value with which it was extracted. So that's just going to be this distance value. Right. So now it's captured, and now it's time to look at the adjacency list. So normally we would say for every neighbor in the adjacency list of node, but here we have pairs. So we'll say for every neighbor comma W in the adjacency list of that node, well, there are 3 options. Right? So if this is my node and I'm looking at a neighbor, there are 3 options for what this neighbor could be like. Option 1 is this neighbor could be a new fish that we didn't know existed, a new vertex that we have not seen before. So it's undiscovered. That's one option. Second option is that it is discovered. It is discovered and it's lying inside the priority queue. And option 3 is that it's captured. So if the neighbor is already captured, that means its shortest path value is finalized. We don't have to do anything. Right? We don't care about that neighbor. But if that neighbor is has just been discovered, it was undiscovered so far, or if it was previously discovered and is lying inside the priority queue, in either case, we would want to insert a new copy of that neighbor with a priority value that tells us what is the shortest path to the neighbor through this node. Right? This node has been captured, so its shortest path value is something we have finalized. So if the path to the neighbor through this node is better than any other path we have so far found, then obviously we want to update the priority value. But unfortunately, we can't go into the heap and update it, which is why we are just choosing to reinsert a fresh copy of this neighbor with that priority value. So that means we care only about whether the neighbor is captured or not. Among these 3 cases, in case 2 and case 3, that is, when the neighbor is discovered or undiscovered, we do the same thing. We will insert a copy of that neighbor with that priority value. So it's only the captured part that we have to check, that as long as the captured value, as long as the neighbor has not been captured, we will add a copy of it to the priority queue, right? So let me say q dot insert. We will insert a copy of that neighbor into the priority queue with what priority value? Well, whatever the shortest path distance to that node was, plus the weight of the edge from the node to the neighbor. And that priority value has to be the first element of that pair. So we are really inserting a pair into the queue. The first element of the pair is the value itself. So the priority value, which is W plus the shortest path distance to the node, which is stored in captured of node. And then we will, the second element of the pair is the ID of the vertex itself, which is the neighbor. Right, this is what we insert. And if it's already captured, then we don't do anything. We just drop that edge. So there's nothing to do here. So this is what we keep executing repeatedly until the queue becomes empty. And when the queue becomes empty, the captured array is going to tell us what the shortest path distances to all the reachable nodes are. If there are any nodes that are not reachable, their captured values would still be -1. So when we exit the while loop here, the last vertex that had been pulled out of the priority queue, that would be the vertex that was farthest from the source, because recall from the foundation videos that Dijkstra's algorithm plucks out nodes from the priority queue in increasing order, or I should say non-decreasing order of shortest path distance values, right? It's a greedy algorithm. It builds the shortest path tree in increasing order of shortest path distance values. So the most recently captured node would tell us on what day it was captured, right? The shortest path distance to that node would tell us what is the day in which everyone has gotten infected. So how do we track that? Well, again, there are multiple ways to do it. Um, um, we could just, whenever a node is captured, we could have a variable which we could call the last or the most recent distance value, or whatever, something like that, the last distance value, which is something we update. The last distance value is basically whatever the distance value, the most recently the captured node's shortest path distance value. That is something we could store. We initialize it to 0 because we know that for the source, that value is 0. And then this is the value that we would want to return as the solution to this problem, provided that everyone has gotten infected. So if there is a node that couldn't be captured, which was not reachable from the source, then we are supposed to return a -1. So we could either traverse the captured array and see if all the values, at least from indices 1 to n, are -1 or not. Or another option is we could just keep track of how many nodes were captured. So I could say that could be a separate variable. Right? It starts out being 0 because there's nothing captured at the beginning. Even the source has been put into the priority queue. So the first node that will come out of the priority queue will obviously be the source itself. And whenever we capture a node, we increase this value by 1. And here we just check if that value finally is n or not. This value is n. By the way, the source here is in this particular problem, the source is the vertex with ID k. So if the number of vertices that have been captured is n, that means whatever answer we had calculated for the last distance value, the most recently captured node's shortest path distance value, that is what we return. But if the number of captured vertices is not n, that means it's some value less than n, that means we couldn't infect every one, then the problem tells us that we're supposed to return a -1. And so that's how we implement Dijkstra's algorithm. Run it just once, starting from the source node k, and at the end return the answer. The complexity in terms of time, as before, is order m log n. I will let you again look at the foundation videos for this. This is not clear. In sparse graphs, m is order n, so we can say this is n log n for sparse graphs. And roughly speaking, why is it m log n? Because every time Dijkstra's algorithm is a general graph traversal algorithm. So it's going to look at every edge in the graph, and every time it looks at an edge in the graph, it could potentially add a new copy of that neighbor vertex into the heap. So that means for every edge that we see, we could be doing log n effort to add that, the neighbor at the other endpoint of that edge into the priority queue. And in the future, that value will also be popped out of the priority queue. That would also take log n time. So the combined work that we are associating with each edge is log n. And so overall, it would be order m log n. Of course, building the graph takes order m plus n time. That's a separate piece of work, but the dominant term is going to be order m log n. The space complexity in this particular implementation is order m in terms of auxiliary space. Of course, the adjacency list itself takes up order m plus n space. So maybe we should add that as well. So the space complexity would be order m auxiliary space for the heap plus order m plus n for the adjacency list. So that's order m plus n in total. Okay, any questions on this? Naveen?
Hey Omkar, so couple of questions. When we are defining the space complexity, in this we see it is O of m plus O of m plus n. We always say the maximum, right? The worst case. So it should be O of m plus n. Is that enough in the interview?
Yeah, O of m plus n
Okay.
is the worst case. I'm just pointing out the heap separately because this is a little more expensive than what the algorithms textbooks present, in which they assume that the heap is storing only one copy of each vertex and that you can update the priority by going into the heap and changing the priority physically there, which is not a facility that library heap functions provide us in programming languages, although it can be implemented in that way, but we would have to implement it on our own, which is too expensive. And so in competitive programming, um, this is the implementation that is preferred, which is fast to implement. And even though this is order m, the other standard implementation would have been order n, which would be a little better, but it's okay to, it's not asymptotically going to change our space complexity,
Mm-hmm.
and it's easier to implement within 10 minutes in an interview. This is a medium problem, right? So that means um, ideally in 20 minutes you should be done discussing the algorithm and writing the code.
Makes sense. The second question I had was, can you explain what is the significance of that if condition? If captured node not equal to -1, continue.
So, um, in breadth first search, um, well, in breadth first search, we didn't care about captured. So let's drop that here. But here, what we are checking is that if the node has already been captured before, that means its shortest path distance value had already been finalized before. Because if there were 5 copies of that node in the priority queue, the copy with the smallest priority value, right, the smallest shortest path distance value, that would have come out first. And that is what would have led that node to be captured. So if you are looking at subsequent copies of that same vertex, those subsequent copies would have higher shortest path distance values tagged with them. And those are irrelevant. Because they are irrelevant, we just, by saying continue, we are saying just move on. I mean, go back and pop the next node from the priority queue, because we know that our heap has some unnecessary entries in it. Right? The only relevant entry for a given vertex is the entry which comes out first with the smallest priority value. The other entries are there just because we could, library heaps don't provide us a decrease key function or a change priority function.
Yeah, I understand now. Thank you.
Kaveh?
Sir, how are you?
Good. How are you?
Thank you for taking those classes. They are so exciting. I was working on another thing. I know it's unrelated, but just something come to my mind on the longest pass, reaching somewhere. So that was one of the practice sets. I was thinking about the shortest pass or even the longest pass. If you consider we do a DFS, and along the way, we just record the distance we're coming and also the path we came to that specific node. And when we reach to our target, we just record it and say, okay, so that's the best so far I find, and that's the path. And then I go to another, like I go one level up and then choose another path to go. And then I end up again to that sink. I'm considering that we are targeting a sink from a source, right? And then when I reach to that sink, I will compare my result to last path that I came. And if it is a better one, then I just replace it with that path. Yeah, I think with that solution, we go order M and N because we just see every node one time and we don't use any priority queue. That makes sense?
No, actually, if what you're referring to is a combinatorial enumeration based approach to find the shortest
Oh,
path,
okay.
right? You try every possible path.
Yes.
And pick the one that is the shortest among them. So
Okay.
you will actually end up spending exponential time if you follow that DFS based approach, because you would have to look at all possible paths. Like I think last time I gave the example of in fact, even in the videos, in the foundation videos, I have the example of a graph which you can see very clearly has an exponential number of shortest paths.
I will go and watch it again. Yeah.
Sure. So yeah, it's correct, but it's too expensive.
Got it.
Because you would have to visit the same vertex over and over along different paths. You may not visit the same vertex twice along the same DFS chain, but across different paths, you will be visiting the same vertex over and over. Just like in permutations and combinations, when enumerating them, we visit this, I mean, we look at the same character or the same integer in the input array many, many, many times.
Got it.
So, yeah.
Yeah, thank you so much. I'm sorry.
No problem. Shankar Narayanan.
Hi, Omkar.
Yeah.
Just a question on the time complexity again. So in the worst case, wouldn't the heap have up to m elements in it? Like, why is it O of m log n and not O of m log m?
Yeah, it is. You can say it's O of m log m, but because log of m in the worst case is log of n square, right? Because m in the worst case can be order n square, and
Oh,
this
okay.
is 2 log n, right? Log of n square is just 2 log n. 2 log n is order of log n.
Okay, got it. Thanks.
So it's, you can say m log m, but it's m log m or m log n. It's the same thing.
Okay.
Melvin?
So I'm thinking again of the complexity of the heap specifically. And what I'm trying to think through, I've not been able to process it in real time in my head, is the size, the maximum size of the heap is not necessarily n because it has repeated elements, right? If there are n nodes, and a node can repeat itself in the heap.
Mm.
And I'm trying to think, what is the worst case size of the heap?
Yeah, that's why order m, because every time, when do we insert an element into the heap? When we
Right, I see.
when we look across an edge and we see a neighbor on the other side,
Okay.
and that neighbor is not captured yet. So that means I mean, the worst case, every edge we look across would have a neighbor that's either undiscovered or visited.
Okay.
And so we would just insert everything into the heap.
So the worst case would be like a maximally connected graph.
Yeah, I mean, imagine a graph where the source is connected to every vertex.
Yes, exactly. Maximally.
So every vertex will get added that point. So all edges get added.
Right.
I mean, that's just one example. There could be
Okay.
other examples of graphs you could construct where it's
Great.
a large fraction of the edges are inserted.
Yes.
Abhishek?
Hi, Omkar. So I have a question around the time complexity again. So when you're saying that m can be at max n square, then why do you take a special case for sparse graphs there? Because if m is n square, then the complexity is again quadratic, right? Because in the worst case, I'm thinking.
Yeah. In the worst case, if it's a dense graph, it's going to be m log n, which is going to be, we can say n square log n. Right? If m can be order n square, it's going to be n square log n. I talk about sparse graphs basically because most real world graphs are sparse. And the complexity being n log n and not n square log n makes a lot of difference, because going back to the things I mentioned this point in the sorting foundations, that when you once you cross n log n and move into the quadratic or higher zone, then the size of the input that you can run your algorithm on becomes severely restricted. With an n log n algorithm, you can still hope to run Dijkstra's algorithm on a graph that has hundreds of thousands or millions of nodes. But if it's sparse, that's okay. But if it's dense, then n square log n means that your graph size has to be, maybe a few tens of thousands at most. Can't go beyond that.
Right. Yeah, because in the foundation videos also you have taken that case always that it's a sparse graph.
Yeah, and as you'll see, I think I won't get to it today, but depending on whether the graph is sparse or not, for some problems the algorithm itself might be different. So I haven't yet come to the all pairs shortest path problem, but you'll see there that the best algorithm for sparse graphs is different from the best algorithm for dense graphs. So we'll have an algorithm called Floyd-Warshall for dense graphs and another algorithm called Johnson's algorithm for sparse graphs.
Okay, sure. And one more question. So is there a specific number we can mention about the number of times we see a particular edge?
Once. In a directed graph, once. In an undirected graph, 2 times. This is an
Okay.
instance of the general graph traversal algorithm. So there's no difference in how many times you see an edge, whether it's BFS or DFS or Dijkstra, or for that matter, even Prim or
Okay, got it.
yeah.
Sure. Thank you, Omkar.
Balaji asked, are you sure that it's correct to do if captured of neighbor is equal to -1 inside the for loop? So Balaji, this is just like in BFS. We would look at every neighbor in the adjacency list of node, and we would check if that neighbor is still unvisited, right? We would mark it as visited, and then we would insert it into the BFS queue. Here we are saying if the neighbor is not captured, right? That means it's either undiscovered or it's lying in the priority queue, doesn't matter. We would still insert a new fresh copy of that neighbor into the priority queue. Does that make sense? The time at which a node is added to the priority queue is different from when we start processing it. Yeah, that's true even for BFS and also true for Dijkstra. But in BFS, not only is the time different, but the value, the shortest path distance value remains unchanged. Right? That's why we put it into the queue. We don't even record the shortest path distance value in the queue because it doesn't change. It's hard coded. So we directly put it into the visited or distance array. Whereas here, until that node is plucked out, we don't know what the shortest path value is because it could change as that node is sitting inside the priority queue. Why would discovered will have multiple copies? Why would discovered will have multiple copies? I mean, when we see a vertex, we will discover it. I mean, let's just go back to that simple graph, right? When we pull out, initially we have S in the priority queue, right? Then we pull it out, we look at both of its neighbors, we see U and V. So what we will do is we will insert U into the priority queue with a shortest path distance value of 2. Okay, I'm writing it as U comma 2, although it will actually be 2 comma U. So that's one thing we'll do. The other neighbor V will be inserted into the priority queue with tentative shortest path distance value as 5. Okay. Now among these two, the element with the smaller priority value is 2 comma U. So this will be plucked out. And when we pluck it out, we'll capture U, and then we will look at its neighbors, outgoing neighbors. What do we see? We see V as the neighbor. And since U is captured, at that point, we know the shortest path distance value to U is 2. 2 plus 2 is 4. So we will insert V into the priority queue with a priority value of 4. So now there are 2 copies of V lying with 2 different priority queue values. And between these two, this is the one that will come out first. So that means when V is captured, it will be captured with the shortest path distance value set at 4. And so when later on the second copy comes out, we don't care about it. We just discard it. We just continue. We just move on. Okay, now this is a simple example. So you could ask for the simple example, well, why couldn't we just go in and change the priority value for V from 5 to 4 instead of adding a second copy? Well, that's because this is a small example. You can think of doing that. But if the heap is huge, you can't search for V inside a heap. A heap doesn't allow you to search efficiently. So this is the hack we do. I just add a second copy with a different priority value. Is there a specific number of times a vertex is added to the queue, or is it correct to say that it depends on the in degree of that vertex? Yeah, it depends on the in degree of that vertex. Because that vertex will be added only if there is a fresh edge leading into it, which has some priority value. We don't know whether it's smaller or bigger, since we can't again search to find that vertex in the heap. Okay, so let's move on to the next problem. This is the code for it. Hopefully not different from what I wrote. I do see that I, for some reason, have a visited array which is actually not relevant here. So let me cut it out. So, and there are obviously variations. You could have maintained captured as just a hash map, in which case you didn't need a separate variable called how many have been captured. Just look at how many are inside the captured set. If that value is n, then you return uh, the value of the day on which everyone got infected. Otherwise, you return a -1.